All right, let's talk about the quantization of charge, and we're going to focus on Millikan's experiment to deduce what exactly is the charge on an electron. In this region, the oil droplets firstly are given a charge. So if we focus our attention on a single oil droplet right there, that oil droplet was given a charge using some sort of ionizing radiation. That's kind of what's shown here. And because of that, these charged oil droplets, which are falling down because of gravity, um, now we can apply a potential difference. You can see there's a battery here, and we can create a potential difference where one plate up here will have one charge, plate down towards the bottom will have another charge. And it is possible then to create a situation where the force of gravity acting down on the oil droplets can be countered by a upward force because of the electrostatic attraction or repulsion, or the electrostatic force because of the electric field created in this region. And I think you can probably see where Millikan's going to go with this. By manipulating the amount of force, the electrostatic force on the oil droplet, he could slow down the rate at which it accelerated down. He could stop the acceleration down and make sure that the net force was zero, in which case this thing would just drift down at a constant velocity. Or he could maybe make it suspend and hover there. Or he could actually increase this electrostatic force to be greater than the force of gravity. And in that case, the oil droplet would accelerate upwards. So it really, when we get down to it, the nuts and bolts of the oil droplet experiment are really right in this region right here, where we apply this opposite electrostatic force to the force of gravity, and by manipulating that, start to be able to do some math to maybe work our way to what exactly is the charge on an electron. So let's look at the mathematical analysis then of the experiment. And there's really three possible scenarios that I've kind of described. Let's qualify them here. We could have, and this is very common in our course, this situation right here in which the oil droplet does not accelerate. And that's because the electrostatic attraction, or the electrostatic force up, is equal to and opposite the force of gravity down. So the equation for the electrostatic force, F equals EQ, and the equation for the force of gravity, we could, in this circumstance, say Fe is equal to Fg in magnitude, one's up and one's down. And as you have seen in the past, this allows us to start to maybe do some calculations which we couldn't prior to this do. We know a lot about forces of gravities, and we can use that to find, in Millikan's case, the charge. Now, be aware, the oil droplet does not accelerate, but it may have a constant velocity up or down. Just because it doesn't accelerate doesn't mean it's at rest. So in this type of question, the acceleration is zero, right? But the velocity could be constant up, down, or zero. Contrast that with the next situation. In this situation, we don't have enough upward force because of the electrostatics to overcome gravity, so gravity is greater. And in this case, the oil droplet will accelerate down, as we can see, although it may have a velocity up or down. Wrap your brain around that for a second. So sure, if we release this thing from rest, it will begin accelerating down and moving down. But if we imagine a case where the initial velocity was already in the upward direction, then it'll take a moment before this thing comes to rest and then begins its downward descent. So don't be fooled. And those people that have a decent memory and are on top of things, you'll have a memory of this from Physics 20. Don't be fooled by the way it's moving at the moment. Don't be fooled by the speed or velocity direction. What we're worried about here is which force is winning in this tug of war, up or down. So in the middle case here, when gravitational force wins, we will accelerate down. So we'll get an acceleration of some amount in the downward direction. Finally, the third possibility is we have a greater upward force than downward force. So the force of electrostatics up overcomes or is greater than the force of gravity down. Again, just a little note down here, it may have an upward or downward velocity. We don't care about that. All we can say in this condition is if that force of electrostatic attraction up is greater, then the acceleration will be in the upward direction, regardless of which way the oil droplet is moving. So this is not brand new, any of these situations. In fact, this should be very familiar to people as very similar to elevator problems that you've seen before. So we've just replaced the elevator with its mass with this oil droplet with its mass. And then we subject it to different situations, but really comes down to the same concept, and that is we will get a net force if the electrostatic force and the gravitational force, considering their directions, one's up and one's usually down, although I guess somebody could get crazy on you and say, hey, instead of applying an upward force here, we're going to make the electrostatic force down as well, and then we'll get a greater acceleration here. But regardless, we can always start with this idea, this big concept of Newton's laws of motion, where the net force, the mass times the acceleration, is going to equal the net or the sum of the forces acting on the object. Electrostatic force, which is going to be Q times E, gravitational force, which is M times G. So keep this in mind. I would suggest that if you start problems around Millikan's oil drop experiment with this premise, net force is the sum of the forces acting on this, and you're careful with the direction, then you should be successful in most of these kinds of questions. If you could do elevator problems and you didn't forget all about them, then you can do Millikan's oil drop experiment questions. So let's take a look at one example. How many electrons are gained or lost by a plastic sphere of mass 2.4 times 10 to the minus 14 kilograms that is suspended by an electric field of 5.0 times 10 to the fifth newtons per coulomb up? Lots of words. Let me make sure I understand what's going on. I'm going to draw a picture of my, it's a plastic sphere, but don't worry, it's an oil drop question through and through. We have our expected and anticipated force of gravity that is in the downward direction. I'll draw in pink the upward force because of the electrostatic attraction / repulsion that goes on here. And as a result of those two things coming together, it is suspended. So we can say that the net force is equal to 0. And so we could jump right into this by making this equality where the electrostatic force magnitude-wise is equal to the force of gravity magnitude-wise. They add up to 0. This plus this equals 0, net force of 0. So we could just go right ahead and say the electrostatic force has the same magnitude as the gravitational force. So the Q times the E is equal to the M times the G. And again, as long as we kind of just look at the magnitudes of these things, we should be good. If we rearrange first, the charge should be mass times the gravitational constant divided by the electric field. So mass 2.4 times 10 to the power of 14, negative 14 kilograms times 9.81 meters per second squared divided by electric field is 5.0 times 10 to the fifth newtons per coulomb. And so those are all the pieces of information we need. We should be able to solve for the charge. Now I get an answer of 4.7. I'll write it out here. It's 4.7088 times 10 to the minus 19 coulombs worth of charge. But the question doesn't ask how many coulombs of charge. It says how many extra electrons or how many electrons have we gained or lost here. Well, we have the equivalent of 4.7088 times 10 to the minus 19 coulombs worth of electrons. Now, we have the benefit of knowing something Coulomb didn't know, and that is we know the charge on an electron. The charge on an electron, also known as the elementary charge on your data sheet, the elementary charge is 1.6 times 10 to the minus 19 coulombs. So we are going to take this value here, do one last calculation. If we have a total of 4.7088 times 10 to the minus 19 coulombs, and we divide by the charge on one electron, 1.6 times 10 to the minus 19. If you want to put units in, it's coulombs per electron. And you'll notice if you put your units in, the coulombs will cancel out. The electrons down here will end up on the top, and we'll get our answer in electrons. And the interesting thing is you don't get an exact number, but here's the beauty of quantization. Even though our answer says 2.943 electrons, we will not write that down because we understand you cannot have 94% of an electron. You can't have 0.94, 0.75, or even half an electron. You either have 2 electrons or you have 3. So we get to make a decision now and know that our answer is absolutely right, regardless of any business with significant digits. We can safely say this 2.943 really is telling us that we have 3 electrons. What about sig digs? Sig digs is for measured values. This is count. This is an exact value. There is 3 electrons on this plastic sphere that allows it to be suspended in this region in space. That's kind of the beauty of quantization. Is as long as you're close, you can round to the nearest whole number. So 3 electrons is our answer. Let's look at a question that's a little more involved than the last one. Like I said, a lot of times we get questions where we suspend charged particles, in that last case, plastic spheres in space, but sometimes they will accelerate up or down in a Millikan style experiment. So let's take a look at an example like that. An oil droplet with an excess charge because it has 100 extra electrons. So if you're keeping track, it has 100 extra electrons, 1.6 times 10 to the minus 19 coulombs for each electron. So we end up with 1.6 times 10 to the minus 17 coulombs. That's how much charge we have. Accelerates at a rate of 2.50 meters per second squared. Down, this is important. So in my picture, I can start with my oil droplet like this. It's got a downward force of gravity on it. It's got an upward force because of electrostatics, but this is smaller and gravity wins and it accelerates down, so we're good there. The reason we've created this field is because we have 2 charged plates, one up here, one up here. They tell us the distance between the 2 plates, and the distance between the 2 plates is 2.0 centimeters. I feel like that might become important at some point or another. We'll find out, because they want to know what is the voltage across these 2 plates. So we have a battery connected here, and it has some sort of voltage between the 2 plates. So we're really going to draw on a lot of physics that we've studied in the past. So keep your eye on the prize here and keep track of what we're kind of trying to figure out, but be willing to draw in from all parts of the course that we've studied so far. So let's check it out. We would like to find out the voltage across the plates. Well, if you can follow the logic, the voltage across the plates creates the electric field. So I'm going to write a couple formulas here that might be handy. One is that the electric field between these 2 plates is equal to the voltage over the distance between the plates. All right, so I can find the voltage if I know the electric field and the distance between the plates. Now I do know the distance between the plates, so it looks like this is really going to hinge on me finding the electric field. Now I remember seeing the electric field somewhere. Remember, the electric field causes the electric force. It's the electric field times the charge, and force of gravity is m times g. And in this case, we do have a net force. We do have an extra force down. So here's what I'm going to do, and I think it works. Like I told you before, for any questions, especially when we do have an acceleration, we can say, just like we did in elevator problems, that the net force is the sum of all forces acting on the object. So it's the electrostatic force plus the gravitational force. I'm going to emphasize, because I know people will forget, they get lazy, or they think, oh, I don't have to worry about it. These vector arrows are important. The direction will be critical here. So the net force we will find by taking the mass times the acceleration. The electrostatic force we will get using Q times the charge. And the gravitational force we'll get by taking m times g. And if you are careful, remember the net force should be down, the electrostatic force will be up, and the gravitational force will be down. So it's always good, even if the math doesn't use common sense, math should point us in the right direction. So, but it doesn't hurt to also logic it out. All right, so let's put our values in here. Mass, let's go back. Oh. Oil droplet, blah, blah, blah. Oh, where's mass? Oh, here it is. Mass is 2.3 times 10 to the minus 8 kilograms. So 2.3 times 10 to the minus 8 kilograms multiplied by a downward acceleration of 2.5, so negative 2.50 meters per second squared, is equal to the charge, 1.6 times 10 to the minus 19 coulombs, multiplied by the electric field. I am looking for that so I can get my voltage, plus the mass, 2.3 times 10 to the minus 8 kilograms, multiplied by g, which is 9.81 meters per second squared, and that is down. So I will end up with a negative value for my net force. I'll end up with a positive value for my electric force, and I will get a negative value for my gravitational force, so everything should work out. So my net force is 5.75 times 10 to the power of negative 8 newtons. Still don't know my electric force, so I'll just put 1.6 times 10 to the minus 19 coulombs times the electric field, plus 2.26 times 10 to the minus 7 or so newtons. That's a negative value as well, so let's not lose track of that. So I think we have all the numbers we need here. Let's do a little more math to get that 1.6 times 10 to the minus 19 coulombs multiplied by my electric field is equal to 1.68 times 10 to the minus 7 newtons. So dividing both sides by 1.6 times 10 to the minus 19, and I get 1.05 times 10 to the minus 12 newtons per coulomb as my electric field. So a lot of work going on here, but just to summarize the principles we're using, the formulas, we're really, in this case, we're drawing from physics 20 and the idea of net forces being the sum of all forces on an object. Then we break this into individual formulas. The net force is mass times the net acceleration. Electrostatic force, we've learned this year, and force of gravity. So the physics is kind of, we've been there and we've done those things in the past. So our last calculation is to figure out our voltage. Let's just move over here and do that. So our voltage, once we rearrange the equation, should be electric field times the distance. So the electric field we just found to be 1.05 times 10 to the minus 12 newtons per coulomb. Multiply that by the distance, which was 0.02 meters, and we can get our final answer.